Yeah, that's what I do. I had all of it. So I got it. I'm Jewish.
Okay, our clock says 1:30, so why don't we get started? Good afternoon, Research Methods. That's pretty good. They're usually about that loud when they're responding. We have a couple of visitors joining us today from Shaker Heights, so welcome to our visitors. We're delighted to have you here at our campus. This is a Research Methods class, and I will put this into context a little bit as we're going on through. Just for the students in the class, what I thought I'd remind us of is that we are here in week number 11, November 5th. Happy Election Day. Has anybody here voted today? Any voters? No? It might be that we have some folks who are not residential, so maybe you're voting by absentee ballot. A lot of people don't have an election today in their hometowns because it's an off election year. But anyway, happy Election Day. So here we are on Tuesday, November 5th, and we'll be talking some more about repeated measures designs. And we'll continue that conversation. And then later on tomorrow, I'll be handing out the assignment that's due on Friday. I think you'll really enjoy this. We'll see how repeated measures designs might be relevant to this important topic. This article came out a while back. It's called Treating Prejudice, an Exposure Therapy Approach to Reducing Negative Reactions Towards Stigmatized Groups. So you don't have to read this one tonight, but you'll be reading this one on Wednesday night and Thursday night to answer the questions that are going to be due on Friday. So the students last year did this one. I think they really enjoyed it. Okay, so that's what we're going for the rest of this week. We'll be talking about the repeated measures designs. And I thought I'd also, especially for the benefit of our visitors today, put us into context a little bit. This is a research methods course in psychology. And what we do in this class is we go through this research cycle time and time again, and we focus on different parts of this research cycle. In psychology, we're always describing three major phenomena: behaviors, thoughts, and feelings. These are real-world phenomena, and we try to investigate these by using some kind of research representation. To get from the real world to something that's a little bit more manageable, a little bit more practical, we have to engage in abstraction. Can our students tell us the two components that we have to abstraction? Go ahead, Jenna, thank you. Okay, right, so we have to operationalize what it is that we're talking about in the real world, what kinds of phenomena, and then we engage in all kinds of sampling. And we've spent some time this semester engaging in sampling to develop a research representation. And then we use any of three broad categories of methodology in order to get some research results. Can we yell out our three methodology types? So I'll yell them out. Surveys, observation, and experiments. Okay, so we're using all of those in order to get some research results, and then we have a whole host of data analytic techniques, including something called repeated measures designs. So that's what we're talking about this week. That will give us some research conclusions that we hope will generalize back to the real world. It may or may not be the case that they do, but that's always our hope. Okay, so that gives us a little bit of context for the conversations that we're having. So on the topic of data analysis, we were doing this one yesterday. Our students can go out and join us if you like on this Excel spreadsheet. This is the one that we finished yesterday. And to set the stage a little bit, again, for Mario, who's visiting with us today, what we did yesterday was a kind of computation called a t-test. Have you heard of those, Mario, or no? Okay. Sometimes when you're running a statistical test, we'll be doing a particular kind of statistical test called a t-test. And here we were looking at the issue of depression. And when we're talking about depression, we might have different kinds of ways of remediating depression. And one technique is called transcranial magnetic stimulation. The idea is that you apply a magnetic pulse to the cranium, and if you do this repeatedly and in the right spot, the claim is that there can be some remediation of depressive symptoms. Okay? So what we have here are some depression scores before the transcranial magnetic stimulation for 7 people. And then we have those same folks after they've been zapped with this TMS pulse, and we get their mood scores, and we do some statistical analysis and figure out whether there's a change that occurs from time 1 to time 2. And because we're making these measurements on the same people twice, we call this a repeated measures design. So that's where we were yesterday. How many students are able to call this one up inside of Excel? You're able to find that? Okay. All right. So what we wind up doing is all this computation, and we try to come to some kind of a p-value over here. I'll label it as such. You can join me in cell G21. We'll call this our probability value, also known as our sig value. This is the probability of making a type 1 error. Will somebody remind us what a type 1 error is? Or students? Okay, thanks, Natalie. Okay, it's a false positive. We might think that we have a positively working manipulation here, or therapeutic intervention. We think that TMS actually is working, but maybe it isn't. What this number specifies is the probability of a false positive. So if we do reject the null hypothesis, which is that there's no effective TMS, then we would be running the risk of a type 1 error. Maybe we're rejecting that null hypothesis in error. Okay, any questions on that so far, or on anything that we did coming up to that point yesterday during our computation? Okay, what I'd like to do now is give us an appreciation for where this t statistic fits inside of this distribution of t-scores. The null hypothesis is claiming that basically TMS doesn't work. Okay, so we would find no difference in the before scores versus the after scores. If we were to difference those, we'd come up with 0 as our difference, or nearly so, either 0 or thereabouts. And we can actually position this particular t at, where's our t value? 3.94. Okay? That t was out here in our rejection region. We were able to reject the null hypothesis. What I'd like to do is something that we haven't done yet this semester. I want to give the class some intuition for just how rare it is that you'd wind up here, out in this rejection region, statistically. And we know that it's 5% of the time, but we want to develop an intuition for what that's like. What does 5% really feel like? So what we're going to do is change the data that we have here to purely random data. Okay? These numbers I had made up before so that we would get an effective TMS. But now we're just going to randomize these data. So if you have this up, would you please join me by clicking on the 5? Okay? And that is cell C7, contains a value of 5. And right now it's a value of 5, but we're going to make that a randomly varying number using a command I'm not sure we've used before. This is called equals. Let's do that, equals. And then we'll put in the words rand between. Okay, we're going to get a random number between some upper value and some lower value. On this hypothetical test for your depression score, we're going to assume that you could get scores as low as 1 or scores as high as 9. So we want to get random numbers between 1 and 9. So we have equals rand between, left paren, let's put in a 1, comma, 9. And then we'll do a right paren. And I'll hit enter. Or I'll let you hit enter. I'll leave that up there so people can see what the syntax looks like. And can you all yell out what number you came up with? The numbers are all over the place, right? Because they're random numbers. I'll do this. I came up with a 3 at this moment. Okay, now if we hold down the F9 key, excuse me, you should get some randomly varying value in that particular cell. And if you hold it down really hard and just keep it down permanently, you're getting numbers between 1 and 9. Show of hands, how many people get that randomly varying number? Okay, so now instead of having just that one cell be a randomly varying number, can we do our trick of dragging down that syntax and getting a column filled with randomly varying numbers? So that little corner of the box, you can grab that down and you'll copy the formula into each successive cell. Okay? Now we have our before TMS scores still in range, 1 through 9, but they're entirely random. And if you hold down the F9 key, you get some random noise there. Who's got that? Okay, that's working. Can we do one more? Can we drag over just one more column? So now we've got the before TMS scores and the after transcranial magnetic stimulation scores, all entirely random. But remember that all of our computations are still in place, right? So now what we're doing is, as we hold that down, we're getting novel data sets that are random data sets, and the t-test is being computed automatically, and we're getting t-values all over the place. Okay? How many people have that? I've got that going on there? Okay, let's do it this way then. We're going to come down to here. This is column G. We're going to work just a little bit with our sig value. Okay? I'll ask you to click on that item, which might be a num for you. It might be a number, or it might have the word num there. Okay? And how many people can see the syntax is equals dist, and then it's cell D21? How many people are able to see that? Anybody not seeing that? Right? You're not seeing that?
My before TMS scores all deleted when I tried to drag them and do random things.
Okay. If you do Control Z, you can get back to where we were. Okay. It'll reposition all that for you, and then we can try to drag again. Okay. Okay. How many people are set up in t-dist, right? You've got the t-dist formula going there. All right, what I'd like to do now is take the absolute value of cell D21, as you see in your formula. So if you go way up top into your error bar, or your formula bar, you have equals t-dist. Can you do a precision insertion just to the left of D21? Make sure everybody's got that. And we're going to put in an ABS, left parenthesis, and then we'll let D21 be in there. We'll put in a right parenthesis. We're taking the absolute value of D21. And D21 was over here, the critical value. Okay. Or excuse me, the observed t value. I'll hit enter. We'll see if that works. And now if we hold down the F9 key, we never get that nasty num. We always get a real value in there. How many people got that to work? Okay. All right. You can help your neighbor if that didn't, but I think just about everybody's there. Catherine, did that work for you? Oh, okay, so we want to do ABS. Here's the syntax up here. Okay, and Katie, can you are you on that, Katie? Did that work for you? Okay, all right, I think everybody's there. All right, so here's the idea. Let's just hold down our F9 keys. We'll let this thing spin for a moment. Everybody's got a spinning, okay? All right, and I'll say stop in a moment, and we're going to see who winds up with a significant F value of anybody, right? 1, 2, 3, stop. Okay, I came up with a sig value of 0.912. Is that significant? That's not significant. Our rule, Mario, for statistical significance here is that if we have a statistic or a value here that's less than 0.05, we say that that's a significant value. Anything greater than 0.05 is going to be a non-significant value. So this is a non-significant difference. Did anybody come up with a significant difference? Okay, so we have something like 16 students in the room. Everybody held it down, and we went over 16, right? Nobody got anything significant. Can you just poke at this thing, hit the F9 once, hit it again? Most of these times, you will not get a significant value. It'll be greater than 0.05. But every once in a while, somebody will come across one just by chance. You got one?
I had a 1.
You had a 0.01?
No, I said 1.
Oh, 1 is not, okay, we need it to be lower than 0.05, okay? Okay, you got a 0.02? So. All right, so if you hold it down long enough, now if you hit it one more time, it'll be gone, and it will take you tell me, about how many hits will it take in order to get one of these on average?
5.
Okay, I hear 5, I hear 10. Let's think about this. The value is 0.05, right? Anybody want to do that? 5 times out of 100, what does that reduce to? 20 times, okay, so basically 1 every 20 times, right, you would get this value being less than that. We'll see how I do. I'm at a sig value of 0.91. Maybe I'll get it the next one. Whoa, okay, nope. 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 4, 5. Ooh, just missed. Okay. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Got it. On the 18th try, mine happened to come up significant. Okay, so if I get to do this psychological experiment many, many times, even if there were no effect of transcranial magnetic stimulation, every once in a while I'd get a significant value just by chance. Remember, these are purely random numbers, rand between 1 through 9. Right? So if you see how rarely that comes up, you have some appreciation for just how far out we'd have to be in these tails, how improbable that's going to be to occur just by chance. Who's following that? Okay. Right? So, and we could now play the game a different way. We could make the alpha level 0.01 or 0.001, and then we'd have to be there for hundreds of trials before we got a value that was significant just by chance. Sometimes when you hold down the F9 key, you get an appreciation for this. Okay, questions or comments on any of that? All right, thanks for playing along in that case. Okay, let's see if we can now go on and talk a little bit more about these repeated measures tests. That was a repeated measures t-test. Can somebody remind us of our motivation for running a repeated measures test or having a repeated measures design? Yeah, thanks, Hannah.
To get rid of consistent individual differences.
Okay, to get rid of consistent individual differences, all right? And what's really great is I think between yesterday and today, almost all of us have memorized that. The advantage of a repeated measures design is it gets rid of consistent individual differences. Memorization is an important component to start, but we actually have to understand what that means. Anybody want to try to elaborate on what that means to get rid of consistent individual differences? If this helps, I think we've used this example. Here's a real baseball player. versus me. I'm not a real player. Okay, Maddie, thank
I
you.
was going to say yesterday you were talking about with hitting the baseballs and maybe like the different colored baseballs, and someone might be a better hitter than you, and that's why they're hitting the colored baseballs rather more than someone else.
Okay, really good. So for our folks in the back, let's see if we can repeat that. And we'll draw a couple of graphs just to make sure that the idea of removing consistent individual differences is very intuitive to all of us. So we're going to pretend that we've been hired as sports psychologists by Spalding, and we're going to use just two colors in this case. They're asking us to evaluate whether white baseballs are as easily hit as green baseballs. They're checking the color of the baseball, and we're going to pretend that we have 100 baseball pitches thrown to hitters, and we ask how many hits they get. Okay, so here's Pedroia. Okay, and Pedroia is a really good hitter, and we're going to draw Pedroia's performance here. This is number of hits. And sometimes we're throwing him, we'll say, green baseballs, and sometimes we're throwing him white baseballs. And this will be 100. This will be 0 hits, and we'll say that he gets 100 hits in the green condition, and we'll say that he gets something like 98 hits in the white condition. I'll put it, this is 98, and that's a 100. Okay, so he's getting a difference of 2 there. Okay? So a really good hitter. He actually just received 200 pitches, and he got 198 hits. That's pretty good. Okay? All right, then it's my turn. Okay? And I'm a stats professor. I'm not a baseball player. So I'm getting the same pitches. All right, so here's me. This is Pedroia. How do you spell Pedroia? I hear it all the time. There it is. Pedroia's up there. That's Pedroia. By contrast, this is me, shown here. Okay, here's green, here's white. Okay, now in come these pitches at a pretty good clip, something like a major league clip, the same one that he got. I get 2 hits in green. That's a 2 in there, and I get 0 in white. Sorry about that. All right. What's Pedroia's difference score between the green and white? 2. He has a different score of 2. What's my difference score? 2. That's weird. Okay. So what Spalding really wants to know is there a difference between green and white? What Spalding doesn't care about is whether a professional baseball player is better at hitting than a stats professor is. So what we've done is we've moved consistent individual differences. We've gotten them out. When we were in the green condition, Pedroia was better than me. When we were in the white condition, Pedroia was better than me. We wouldn't want to have this as our level of variability, right? That's really kind of uninteresting. That's a consistent individual difference that might be interesting to me and Pedroia, but Spalding, who has hired us as sports psychologists, really wants to know what is the hitability of their different products, their green baseball and their white baseball. So by subtracting, we were able to get rid of consistent individual differences and look at the genuine effect of interest, in this case, the effect of ball color. Who's following that? Okay, so that's the beauty of this repeated measures kind of design. We don't really care that one of our participants is better or worse than another one. We really want to get to what's the independent variable doing for our dependent variable? What's the effect that we want to know? Go ahead, Rachel.
So if it weren't repeated, it would be like...
Good, let's take that case. If it weren't repeated, okay? Can somebody step us through? If we had done this, so right now we only have 2 participants, but let's just say we had the same 2, and we didn't use a repeated measures design. We instead used a between subject design. Can somebody tell us how that would go?
Would that be like he hit like the green ball and you hit the white?
Okay, right. So let's say we throw him the green balls, and he's going to get 100 of those, and you throw me the white, and I get 0. Okay. Now you would conclude that green is more easily hit than white, and you would happen to be right, but you would be right for the wrong reason. Okay, because you could have done it this way. You could have thrown me the green balls, and I'd get 2 hits. You could have thrown him the white balls. He'd have 98 hits. You'd falsely conclude that white was the more easily hit baseball. Okay. So the reason we came to that false conclusion is because we had no control over consistent individual differences. Does that work? Okay. Now, if you have a sufficiently large population, you would imagine that there would be a couple of Pedroias that could be randomly assigned here and a couple of Pedroias randomly assigned here. But frequently, you don't have a really good sample. You're working with a more limited sample, and so it's ideal to get rid of consistent individual differences. Okay. So what we've done is we've shown how just by subtracting, we can get rid of consistent individual differences, right? Just by differencing these scores, and we can now get to the effect of interest. And we did this using a very simple bi-level design. right, where we have two levels of our independent variable, the green ball condition and the white ball condition. Now what we're going to do is we're going to pick up on where we left off yesterday when we began to approach the condition, the situation of the Anova. When did we use the Anova? Can somebody remind us? The analysis of variance? So the motivation for using an Anova? There it is. Natalie's got it. When we have more than two. So here we have a mean for the green condition, a mean for the white condition, but suppose we have a whole bunch, okay? Then the differencing becomes a little bit more ambiguous, right? How do we go about doing that? So let's see if you can join me now in PowerPoint. We'll go to yesterday's presentation, and we'll be up to part number 4, where we still have a repeated measures design, just like this is a repeated measures design. But now we're dealing with many, many more than two conditions. Here we had two simple conditions, green versus white. But now with the Anova, we could do that, but we could do more conditions if we wanted to. Okay? So there are some similarities between this kind of setup and our between subjects analysis, our independent groups analysis that we had done before. In each case, we're going to be forming an F ratio. That's shown over here. Okay, this is our F distribution. And we're going to have some kind of between variability over within variability. But now it's going to be between conditions over within conditions, rather than between groups over within groups. Okay? So where we used to say groups, we now say conditions. Who's following that? Is that working for us? Okay. And the reason why we say conditions rather than groups is in a repeated measures design, we only have one group. And every member of that group, as I think Brittany pointed out to us yesterday, receives all levels of the independent variable. So you'd be receiving the green baseballs, the white baseballs, red and blue if we had those conditions as well. Okay? Who's all right with that? Okay, really good. So here's one way of doing that by pie chart. We can talk about partitioning this big variability. Right? We're going to get our sums of squares, as we've done several times, and we can begin to partition that and ask what goes in the numerator, what goes in the denominator. The numerator is green between, that's our working mnemonic, our working memory device. And you can see that we have a relatively large between group variability, or between condition variability, and a much smaller within condition variability. If we put green over red, we're going to come up with some ratio that's going to be substantially larger than 1. Who's following that intuitively? Anybody lost by that? Yeah, okay, so what we're going to do is we're going to come back to that F ratio that we've done several times before, okay? And we're going to have some kind of variance between groups, that's going to be our numerator. And we're going to have some kind of variance within groups, that'll be our denominator. Here, we're actually not talking about groups, though, we're talking about conditions, like maybe the green condition versus the white condition, okay? So in this particular case, we now have some between condition variability shown here in green. It's a relatively large slice of the pie. Big number in the numerator, smaller number in the denominator is going to give us some ratio greater than 1. Okay? And here's the F distribution, and this is where we would be if we had a ratio equaling 1. Okay? But then as our green area is growing, the difference between the groups begins to grow, or between the conditions begins to grow, and then we move further and further out here until eventually we come up with a really big F value, and we can reject the null hypothesis in that case. Does that work for you, Rachel? Okay. All right. So for any Anova, the denominator is called the error term, as we've talked about before. And good experimentalists like you are always trying to reduce the error term. We're trying to reduce that red area and see if we can get a better measure of what's going on. So the advantage in using the within subject design is we can remove those consistent individual differences and take them out of the denominator. Okay? So here's the other example that we talked about in our video. For Mario's benefit, all of these lectures are pre-recorded and people watch them on YouTube before they come in. So they've already seen these slides and we're just practicing a bit here. Okay? And one of the points we make in the video is you can imagine that Pedroia and I might be having a bet, or Homer and Bart might be having a bet about who's the better hitter. But as scientists, we don't really care about that. We're interested in what's going on with our independent variable. And we'd like to be able to pull out this consistent individual difference. Over here, we did that by subtraction. Right? We just differenced Pedroia's scores, we differenced my scores, and we came to the real effect of green versus white. That's what we're doing over here in the Anova, but we need to somehow have a way of pulling out those differences across many, many different conditions, not just two conditions at a time. Okay? All right, so this will give us more statistical power. Somebody want to remind us what statistical power is? It's been a couple of weeks since we've mentioned it. So I can understand that it might not be on the tip of your tongue. Statistical power? This is the capacity to find an effect if there is an effect. Remember that it could be the case that the green versus white difference doesn't do anything. Another possibility is the green versus white difference really does something, but it's a relatively small effect and we miss it. So our capacity to find an effect, if in fact one is there, is called our statistical power. And we're always hoping to increase that. And here we can increase that by removing consistent individual differences from our red area. Okay? By pulling that out, just like we did over here through subtraction. And if we can shrink down that red area, then this component gets smaller. And when that denominator gets smaller, our F ratio gets bigger, and we have a better chance of rejecting the null hypothesis, finding an effect if it's there. Who's following that? Yeah? Anybody lost by that? Okay. So what we did a moment ago is we differenced. Now what we have to do is come up with some other mechanism for pulling that information out. And what we'll do in order to pull that out is introduce the S basic ratio. Okay. So before I go any further, we'll just see if anybody has a question about those pie charts, and then we'll take a look at this new basic ratio. And this is on yesterday's handout, so we'll ask you to pull that one out. You've got it. Okay. Some of these basic ratios are Y, A, and T. Today we're introducing a new one, and Katie has a question.
So why does increasing, or why do you increase statistical power by removing consistent individual differences?
Good. So why do we increase statistical power when we remove consistent individual differences? Let's go back to a couple of things here. We'll leave that up, and it might help if I take, well, I'll draw it over on this side. The F ratio is equal to between variance over within variance. Does that work for us? That much okay? And so whenever we can shrink down the denominator of any kind of a ratio, then the value of that ratio tends to go up. If our F statistic is getting larger and larger and larger, we've got a better chance of rejecting the null hypothesis over on this side, and that would mean we have a better chance of finding an effect if one is actually there. Does that work? Yeah. Okay, really good. Very good. Okay, so as you can see on the handout that we have from yesterday, lots of basic ratios. We've already done Y, A, and T. Now we're introducing a brand new basic ratio called S on our handout, and this will be for removing consistent individual differences. Sadly, this is far less intuitive than this example. This gives us an idea about how differencing can remove the consistent individual differences between me and Pedroia. Okay? If we have lots more participants and we have lots more conditions, we need a faster way of doing that, and that's what this basic ratio S is going to do for us. But it's still the same idea. We're still going to be throwing away the consistent individual differences, which were previously represented in our denominator, and we'll make our F ratio bigger and more sensitive in that way. Okay, so here's our question, and we've been dealing with this one. What's the major advantage? And Hannah has already answered that for us. It's removing consistent individual differences. So we introduce the S basic ratio, okay? And we'll be able to remove this from our denominator. Here it is computationally. We're going to wind up taking the sum of squared row totals, divide by the number of conditions that we have. Here we had only two conditions. We had a green condition and a white condition. But when you get into actual experiments, it might be far more complicated than that. Right, so you divide by, maybe 17 if you had 17 different conditions. Okay? All right, and the way that might look over here inside of Excel, if we did have this inside of Excel, we'd start out with all these different scores for maybe 4 different baseball colors. In addition to green and white, we might have red and blue. Okay? And we have different subjects going down here. This might be Pedroia, that might be me. This is our 3rd, 4th, and 5th participants, and we could go on down the line. This is a squared version of that, as we've done before. We're going to wind up taking these squares, summing those up, and dividing by the number of conditions. Okay? And that's going to give us this S basic ratio. Okay? And then once we have that, we have to factor that into our F table somehow. Let's flip over to this side. People can see that side. Okay? Okay, you've got something like this. And we're going to have now almost its own variable. We can almost quantify how much of the total variability is driven by the differences that we have between individuals. And we'll take that out of our error term. You'll see that the S value is being subtracted. Okay? So that's where our subtraction is. Over here, we're just differencing these two. Over here, we're subtracting out the S statistic. We're making the denominator a little bit smaller. And by doing that, we hope to make this a little bit more sensitive. Okay? All right. So that's a little bit less intuitive, right? Taking all these squares and so forth, that's less intuitive, but it's the same kind of idea. The idea is we're removing consistent individual differences. Who's following that intuitively, even if all the computations are not making sense just yet? Okay. Looks like we're doing okay on that. All right, what I'd like to do is we won't do those computations today, but we'll do them tomorrow. We'll put them into Excel and we'll work through all those sums of squares. We'll see if we can follow that formula tomorrow in class. I did want to spend some time today making sure that we got to the next PowerPoint, but I just thought I'd ask one more time for any questions on the 11.4 PowerPoint, the PowerPoint from yesterday. Yeah? Yeah, please.
The Anova is like, it's like comparing the mean, like more than two means, right?
Uh-huh.
So is it the same thing as like a t-test, or just like looking at more than one?
Yeah, it's very similar to a t-test. There's a relationship between the t-test and the Anova. They're similar to each other in that they're both comparing means. And they're asking basically this question. Let's draw the mean of the first condition, the mean of the second condition. We'll put some error bars on those. Okay? And if the error bars are non-overlapping, we've got a pretty good chance of saying those are statistically different from each other. When the error bars begin to overlap, they're probably not different from each other. Here, I've got two hands, so I can talk about a t-test really easily. If I had a third hand, it would be over here, and I'd be talking about an Anova, where I could now make that comparison of means across more than two conditions.
Okay, and then this one, doing the within subject?
Yeah.
Is there between subjects?
Yes, and we actually did that one last week. Okay, right? We did that one last week, right? So now we're learning about the benefits of having repeated measures within subject Anova. Okay, right? All right, really good. Okay, let's do it this way. On the video, I was giving you the opportunity for an extra credit question. So I think I'll give you an opportunity for extra credit also. Can you take everything off of your desk? You can put your Slater box number up top. This will not be a pop quiz. So if you miss on this question, you don't lose any points. But if you get it, you gain points. Okay, so you're in a sweet situation here. All right? So everything off of your desk. And we'll see if you can make this response in a couple of minutes. We'll give you maybe 2 sentences. Okay? I think you'll see that 2 sentences will come really, really clearly for us. So in your own words, and in no more than 2 sentences, can you answer this question? What do the Mauchly and Bonferroni tests do for us? What do the Mauchly and Bonferroni tests do for us? Even 1 sentence is fine, no more than 2 sentences. And when you're done, you can put that on the back table. So when did you get in today? Did you get in just a little while ago, or have you been here all day? Oh, really? Oh, good. Oh, good. Okay. Did you get to eat in the dining halls at all? Okay. Oh, sure, sure. Right. Oh, good, good. Have you thought about what you might want to study, or are you wide open to it? Oh, good. Okay. I also work in the neuroscience program here in psychology, and so I have some students who are pre-med, and they're interested. Maybe some of them are interested in psychiatry. Some of them are just. I think it's really good. We have a lot of students who are very ambitious and they start out that way, and then some of them find out that it's not for them, but there are lots of courses to take, and some of them come my way because of my connection to neuroscience. But most of them in pre-med are not also neuro-related, but some of them are. So I see a good number of them that way. Yeah.
There was a certain amount of neuroscience that you have to take before you go next.
Actually, I'm not sure if they are now requiring psychology, interestingly enough. As of next summer, or maybe it's 2 summers from now, you have to take a psych course. You don't have to take the course, but there will be a psych component on the MCAT. So yeah, right. Right, and that's new as of I think the summer of 2014. Yeah, yeah. Lucky you, right? All right, we'll see how they're doing here. How are we doing? People doing all right with Mauchly's and Bonferroni? Anybody else? I think that's the whole gang. Okay, so let's go ahead and we'll get into the 11.5 bit. Okay. And here's our research cycle again. Right, we're still on the topic of data analysis. We've been doing these t-tests, these Anovas, And now we'll try to understand this a little bit more thoroughly. As we get into the Anova, so we're doing more than two conditions, right? Here's my first condition, my second condition. If I had a third hand, it would be over here. We'd be measuring that. We have some assumptions that underlie this. Can anybody begin to tell us a little bit about the assumption that underlies within subject Anova? This is part of the video. Thanks, Kip. Go ahead. Yeah, it's hard to say. Let's first get that word down. Can we all say sphericity? Everybody? Sphericity. It takes a little practice getting that. Sometimes our speech is just a motor skill, right? And so sphericity is a bit of a mouthful the first couple of times that we say it. Anything that you want to say about sphericity? That's the correct answer. Yeah.
Yeah, it's the assumption that the correlations among scores in the various conditions are equal. So essentially that different conditions will correlate equally with each other, or with one condition as they will with another condition.
Okay. Okay, that's exactly right. So very nicely stated that the correlations among conditions are going to be roughly equal to each other. This was a little bit similar to something that we've done before in the between subject case. Rachel asked a moment ago about the between subject ANOVA. Anybody remember what that assumption was about? We made a different assumption. It wasn't about sphericity, it was something else. Anybody remember either what that assumption was or what the name of the statistical test was that we had to satisfy? Yeah, please go ahead. Equal variance assumption, right? So we had an equal variance assumption with something. And what was the name of the statistic that told us about that? Can we yell it out? Levine's, okay? So this is very similar but not identical to what we're doing here. We had a two-step process for evaluating the ANOVA in the between subjects case. First, we had to take a look at the assumption. We had to make a statistical evaluation of that assumption using the Levine statistic. And if the equal variance assumption was satisfied, then what did we do? Somebody remind us of step 2? Yeah, thanks. That's right. Then we look at whether or not we retain or reject the null hypothesis. So we evaluate the variances first, and then we evaluate the means. Okay? And our rule is always that 0.05 number that we had at the top of today's conversation. If that's less than 0.05, we reject something, either an equal variance assumption or maybe rejecting the null hypothesis. Same kind of a structure, still 2 steps, but now we're going to swap out the earlier assumption and swap in a new assumption. And that new assumption is called sphericity, and Kip gave it to us just right on target. He was correct in saying that we have these maybe 3 different conditions, A, B, and C. And we can run correlations across pairwise comparisons, the correlation between A and B, the correlation between B and C, the correlation between A and C. And if those correlations are approximately equal to each other, the sphericity assumption is going to be satisfied. When they're very, very different one from the next, then we probably have a violation of sphericity. Who's understanding that intuitively? Okay? And so what was the name of that test that we use for evaluating sphericity? Let's yell it out. I see Rachel's mouthing it. Mauchly's test. Okay, Mauchly's test, which was part of our extra credit question today, right? So instead of looking at the Levine statistic, we'll take that introductory step of looking at the Mauchly. So out goes Levine, in comes Mauchly, but it plays roughly the same role. We're evaluating an assumption in either case. Who's following that? All right. All right, so that's the basic idea. Now, I wonder if somebody would walk us through. Let's go over to here. So here's the homogeneity of variance. This was the Levine test. We did that one last week. This was our cholesterol count example from last week. Okay. Now we've got the sphericity assumption, and we're looking at the correlations that Kip correctly described for us. Here's the Mauchly test. Okay. And we've got some factor, some independent variable, and we wind up with a Mauchly's value over here. That's going to be 0.00, and because it's less than 0.05, we reject the null hypothesis. Who's following that? I should reject the sphericity assumption, I should say. Okay, so that's working for us. All right, and then we come to this kind of a bit. Can somebody walk us through this? This was busy, but we did this on the video. It's a very busy output. Okay, thanks, Katie.
Well, you look at the factor one. You look at the Mauchly's test and
Good.
you reject
Okay.
the hypothesis.
Uh-huh.
But if you reject it, you look at this greenhouse Geisser.
Excellent. Okay. So if we had retained sphericity back over here, which is to say, had this sig value, this probability of making a type 1 error, been greater than 0.05, we could assume sphericity. And if we could assume sphericity, then we'd move across on this line for our first factor, and we'd find that our sig value was less than 0.05. We could reject the null hypothesis. Okay, that's the equality of means hypothesis. Who's following that? Is that working for us? Okay, but if we can't, because we had a rejection of the sphericity assumption, then Katie's pointing out we're going to, as a rule in this class, we'll go with the second one down. This is called the Greenhouse-Geisser adjustment. And what this will do is it will alter the degrees of freedom, and that makes it a little bit harder to beat the number to beat. Over here in our F distribution, we have to make it past this. And because we have a sphericity violation in this particular case, we get penalized. And if we get penalized, this thing basically comes back this way, and it's harder to beat the number to beat. And so instead of having a sig value of 0.000, we might have one of 0.001. So it didn't matter very much, but in principle that could have been a much bigger penalty, and maybe we would have gone all the way to non-significance. That might have been adjusted all the way up to 0.05 or 0.06 or 7 or something along those lines, a really big number, and then we would not be able to reject the null hypothesis. Who's following that? Okay, I see a couple of confused faces. How many people feel a little bit confused by this? And you, okay, this happens every year when we get to this point, because there's a lot of decision making here. I wonder if we can ask Hannah to maybe articulate a question or just say where you got lost.
Yeah, I get when you go down
Good.
the next row.
No, we go down the next row, yep.
Um,
And we're going to follow it across.
I don't know what you do in that.
Okay, good. So what happens when we go down to the next row? So if I can just get us ramped up to that point so far. Okay, so let's remind ourselves that we're doing a two-step process. The first bit was to ask, do we retain or reject the sphericity assumption? In this particular case, Hannah, we actually had to reject the sphericity assumption because this thing was less than 0.05. So far, so good? Does that work for us? Okay. So now we can't use the top row where we would have assumed sphericity. We have to do something else. And what we're going to do in our class is use the second row. And so far, that sounded like you were following that much. Now the question becomes, what do we do on the second row? And as always, we go to the sig value. And the sig values, the second row's sig value is 0.001. Does that work? That still happens to be less than 0.05. So we could reject the null hypothesis in this case. Does that work? So we're always playing by that rule. That never changes. We always go to the sig. If it's less than 0.05, we reject something. Sometimes we're evaluating an assumption. Sometimes we're evaluating an equality of means hypothesis. Here, we're evaluating equality of means using the Greenhouse-Geisser. And we had to use the Greenhouse-Geisser because we had our sphericity violation, right? And so that number is 0.001, but it didn't have to be, right? It could have been the case that that number would have been, 0.09 or 0.5. Right, that would have been higher than 0.01. Does that work? Not really?
Oh, yeah, I get it. I just
Yeah, there's a lot of sig values over here. So life used to be easier, right? It used to be the case that we got one sig value. Let me show you an example. There's only one sig value there. That's easy. If that's less than 0.05, we reject. If it's greater than 0.05, we retain. Now we've got this crazy sphericity assumption going on, and life gets more complicated. We have any number of sig values to choose from. Which one do we pick? How do we know? So our rule will be that if we can assume sphericity, we'll stay on the top line and go with that one. If we can't assume sphericity, we'll drop down one line and we'll pick up that one. Please go ahead.
So is this like the second step where we can tell, because we've already rejected the assumed,
That's right. This is step one. This is step two. Okay? So over here, we have to figure out, do we accept or reject the sphericity assumption? And then based on what happens there, we have to figure out, do we go on line 1 or line 2? If we can assume sphericity, it's top line. If we can't, we assume the second line. We go with the Greenhouse-Geisser, and that number will be the number that tells us whether we're cool or not to reject the null hypothesis. Okay? All right. Other questions or comments? That's a very busy screen, right? That's a very busy output, so it's perfectly reasonable. We'll go with Rachel first and then with Katie. Go ahead.
So we're doing an Anova, and that's comparing like multiple meanings
Good.
within subjects, and then this is this.
Sphericity is hard to say.
But it's like, is that separate from? Or like, I don't know. I'm just confused.
Good.
as to, like,
Good. So we want to compare multiple means, right? Instead of having just the green and white conditions, we've got green, white, red, and blue. Now we've got a whole bunch of conditions, okay? If you're going to run an Anova on that and compare all those means simultaneously, deep, deep, deep in the heart of the statistical analysis is this assumption called the sphericity assumption. I would be delighted to share with you many pages of graduate school text that go into the sphericity assumption. But instead of doing that, what we'll do instead is just say, fortunately, Mauchly tells us which way to go with that. Do we assume it or do we not assume it?
So could you like run an Anova
you might do it this way. You don't really know whether your ANOVA is valid or not until you know whether the assumptions that it rests on are valid. And so we have to figure out are the assumptions good or not so good? And that's what our first step is. And our sphericity assumption here has been violated. We're rejecting it because we're less than 0.05. Okay? So then we probably shouldn't be using the regular line. We have to use some alternately adjusted line. And there are different statisticians. Greenhouse-Geisser is one kind of statistical adjustment. There are other ones that you can see here. And after having made that adjustment, it turns out that we got lucky. We could still reject the null hypothesis, but it didn't have to be that way. Okay? We just happened to get lucky this time. Okay? So yeah, some decision making inside of some really busy graphs here. Please go ahead, Mira.
So if you reject the null hypothesis, then the amount
Yep, okay.
one with just one thing. Is it possible to retain the null hypothesis?
Yeah, these are independent ideas. Let's do this. We have step 1 and we have step 2, right? So step 1 just tells us whether the assumption is safe or not. If it is safe, then we can proceed to evaluate the null hypothesis here. If it's not safe, we have to drop down one line and evaluate the null hypothesis. The idea is that these numbers could be very different from each other, depending on how severely we violated that. And we need many, many pages of graduate text to figure out how Mauchly makes that computation. We're going to take Mauchly's word for it here and just let Mauchly point us in one of two directions: sphericity assumed or Greenhouse-Geisser. Okay? Please go ahead.
So is it like whichever, whether or not it's assumed, like that's what sig value you use to reject or retain?
That's right. So over here, we are doing first the sphericity assumption, right? Okay. And if we wind up rejecting, then we're on Greenhouse-Geisser, and if not, we're up top. Okay. So we have to use, and fortunately, all of these turned out to be rejectable, right? But it won't always be that way. You could have a different data set that sometimes some of those are below 0.05, some of them are above. Which one do we use? And the answer is, it depends on what Mauchly told us about sphericity. Okay? Yep. So it's kind of like this. I think there's a German expression that goes something like, a person with a watch knows what time it is. A person with two watches can never be sure. Okay? Same thing over here. Life was easier when we only had one sig value. Right? Now we have a whole bunch of sig values. Which one do we use? And we figure that out depending on which way Mauchly is pointing us. Okay? Mauchly will point us either to the top row or to the second row, Greenhouse-Geisser. All right, really good. Okay, so that's that one. Why don't we spend just a moment on Bonferroni? Okay, we'll talk a little bit about that. Can somebody, we'll take that one down. Can somebody tell us what the Bonferroni does for us? We learned a little bit about Mauchly. Why don't we see what Bonferroni is doing for us? Anybody have an idea about that? We'll go with Jenna this time.
It controls for cumulative type 1 error.
Okay. Excellent. So this controls for cumulative type 1 error. Let's take a step back. First, who remembers hearing about cumulative type 1 error before? Okay. Anybody want to call out the names of other kinds of tests that we've used to control for cumulative type 1 error? We had 3 of them before, but we haven't mentioned them in about a week or so. So before we got to the Bonferroni, we had other kinds of cumulative type 1 error adjustments. What were those called? Yell them out if you know them. I'll give you one. Tukey. Kind of a French pronunciation. There it is. It's bubbling up. Schaefer? No, but it's almost Schaefer. Chaffee? Okay, Chaffee. Okay, and done it. Okay, and we would use those if we have a between subjects design. Now we have a within subjects design, and SPSS doesn't allow us to compute this post hoc adjustment automatically. We have to do a manual Bonferroni correction. Okay, somebody want to help us through how we make the Bonferroni correction? Anybody remember that trick from the video? Okay, thanks, Jenna.
You take your observed alpha level or your sig level,
Uh-huh.
and you multiply it by the number of t-tests that you do, and then you compare that number to 2.05, which is your expected
Excellent.
alpha level.
Excellent. Okay, so all we're going to do here is we're going to be scaling up our observed alpha level. When we started out today, we had the sig value that was in one of our cells, and we were always looking at that to see if it's 0.05 or not. We're going to now take that value and multiply it by the number of t-tests that we've actually compared. Okay? So we might have an Anova that looks across, how many flavors does Baskin-Robbins have? Was it like 29 or something like that, or 31 flavors? I don't even know if Baskin-Robbins is still around anymore.
Is
It is, okay, okay, all right. And it's in your hometown? How many, and sometimes I say Baskin-Robbins X flavor, like 31 flavors or 29 or whatever it is, okay? So we're gonna test 29 or 31 different flavors, and then we're gonna compare them pairwise to each other. Maybe we make 5 or 7 pairwise comparisons. Let's say we make 7. We would multiply our observed value by 7, and then ask the question, are we less than 0.05 or not? Okay, so let's try, let's see. Should we try one of these? Oh, you know what? It's 2:20. Why don't we give you time off for good behavior? Okay, we'll come back tomorrow. We'll work on the Bonferroni, and then we'll do some manual computations inside of Excel. Okay? Thanks for a great session. See you tomorrow. And if you haven't voted and you want to vote, please vote.